We present controllable human motion generation from trajectories, a general framework that enables an interpretable way to animate people. Animating people is a crucial part of the industry. We need human animations in movies, games, VR systems, and many others. However, achieving a realistic human animation is a long-standing problem that is difficult, time-consuming, and expensive. The animation is often obtained by building a skeleton manually and keyframing each of the joints or using a costly motion capture rig. To semi-automate the animation process, current approaches generate plausible human motions with machine learning models. However, they are limited in two significant ways. They can generate only walking-related motions or provide little controllability over generated animations. To address these issues, we show Trajevy, a versatile model that allows us to input a single trajectory, multiple trajectories, or no trajectories at all to generate complex human animations. In principle, our method changes the workflow of the human motion animation. It requires only an initial skeleton and any number of trajectories. The animation itself is left to the neural network. Our approach not only generates realistic human animation, but also enables recovering missing joints in tracking systems. While we show our results on Stigman figures, the model generalizes to parametric body models as well. Our key insight is that predicting poses from trajectories can be stated as a pose-completion problem. It means that we can represent a sequence of human poses as a sequence of trajectories for each skeleton's joint. We randomly subsample the set of trajectories during training and ask a neural network to complete the missing joints locations. We construct Trajevy as a conditional birational autoencoder. It takes trajectories or future poses as an input. We note that trajectories are represented as future poses with missing joints set to 0. Each time step and the initial pose are processed with MLPs and then passed to a transformer-like layer. We apply discrete cosine transform that allows us to obtain independent representations for different motion frequencies. These are passed to a transformer-like layer and fully connected layers that produce parameters of a normal distribution. The decoder performs the inverse discrete cosine transform, concatenates these codes with the initial pose coding, and outputs joint offsets between poses in consecutive time steps. During training, we process future poses instead of trajectories, where part of weights are shared between both representations. Then we use distinct layers of the same architecture to produce parameters of the normal distribution of the latent representation. The network is trained to minimize the reconstruction error of poses and to minimize the distance between distributions of trajectories and future poses. Therefore, during inference we can use only the part responsible for trajectories without degrading the performance. Once trained, it reconstructs correctly human motion even if only an initial pose is provided. When we add trajectories progressively, the quality improves. We can also freeze the motion by giving the same coordinate each time step. Since we constructed Trajevy as a variational autoencoder, we can sample diverse human animations. The fewer trajectories are given, the more varied the sequences are. When we use the expected value of the latent codes, the generated motion follows trajectories more faithfully. Finally, we show that our approach generalizes to other than walking motion, such as waving, bending, or sitting. In comparison to baselines that we built upon our key insight, Trajevy achieves the best reconstruction quality, where K is the number of trajectories, APD is the measure of the diversity, and ADE and FDE describe the quality. We also compared Trajevy with methods that base their predictions on many past frames during inference, but do not allow controlled future motion generation. When we provide free trajectories, our method already obtains better motions than related works. Thank you for your attention. I'll be happy to answer your questions.